So we are doing complex exponentials, complex logs, and complex powers. The first thing that we need to know that we can actually do the ln of a complex number. The ln of a complex number. So recall again that a complex number in modulus argument form is cos theta plus I sin theta times r, or z is re to the I theta, where the modulus is r and the argument theta. So what we're going to do here is ln z is in Euler form, or in polar form, it's ln r e to the I theta. Now, when we do our ln laws, ln of a product is a product of a limit of ln. So ln AB is ln A plus ln B. If you recall that from first year. So here we have ln r plus I theta ln E. Using again our ln law, ln E to the m is m ln E. And recall that ln E is 1. So now theta is the argument of z plus 2n pi. The argument can be increased by any number of complete revolutions. Hence the 2n pi, where n is a natural number. So that is our argument. When we sketch ln z, recall that the real part of ln z will be ln z modulus, and let's make that in blue, the imaginary part of ln z, everything that's attached to the I, is ln z plus 2n pi, where n is an integer. So what we'll see later is that our real part stays the same. It is ln z. But what will happen to our imaginary part as n is increasing? It will either, in increasing positive, it will increase on the y-axis. So say this is n equals 0, n equals 1, n equals 2, n equals -1. But we'll do an example of that later. So what is very important is that the principal value of ln z, the principal value of ln z will just be ln r plus I theta. Recall that the principal value of the argument of z is between -pi not included and pi included. Then just for later, what is very important is ln z. We can also change it so z is x plus ry. When we split it, we get our real part and we get e to the x e I y. So it is in the form of r e to the I theta. So in this case, r will be ex and theta will be y. So now, let's for now do an example how to evaluate sine of, this is our angle. So I want you all to make sure you study these formulas very well. So this, recall this is Euler, e to the I theta cos plus I sin theta, e to the negative I sin theta cos theta minus I sin theta. So remember that if we have e to the I theta, e to the negative I theta, these two will be complex conjugates. Just keep that in mind for later. And then I want you to study all these formulas, even the hyperbolic. And then, like I said earlier, the Lin laws are very important. So is this e to the m ln x. We take that as an exponent, and then we cancel e and ln, very important for later. So make sure before you start with the examples that you study your theory very well. Because while you do example, you shouldn't look back at your theory. You should know your theory already well. So recall that sine theta is e to the I theta minus e to the negative I theta over 2I. Just a reminder that cos theta is e to the I theta plus e to the negative I theta over 2. No I. Now we see in our example that theta is 2 pi over 3 plus I ln 5. Hence, we will replace our theta every time by this bracket. So we did substitution there. Now we are going to distribute. So we get e to the 2 pi I over 3. And then if we distribute, I times I is I squared, which is negative 1. And then the same here, when we distribute, we get e to the minus 2 pi over 3 and e to the ln 5. Recall that I squared is negative 1, negative I squared is 1. Now, we need now to evaluate this part, e to the 2 pi over 3i. So from Euler's formula, it is cos of the angle plus I sine of the angle. Now, if we have 2 pi over 3, just recall what do we do here? You look at the closest number to 2 pi that is divisible by 3. The closest number to 2 pi is 3 pi. But we know that 3 pi minus pi is 2 pi, and you split the fraction. Just to repeat, you look at the closest number to 2 pi that's divisible by 3. It's 3 pi, and 3 pi minus pi is 2 pi over 3. And then I split, so I have pi minus pi over 3. So, and then I do the same for sine. I do the same here. So I get the same angle here. Now, very important, cos in this quadrant is negative, second quadrant. Hence the negative cos pi over 3. Sine in this quadrant is positive, hence the positive. Then cos of pi over 3 minus a half, the negative, that's where the negative comes from, and sine of pi over 3, root 3 over 2. So I suggest that you learn your special angles. Maybe it's best to use these one. Study them well. It's much better than the fan that I see most students still use from school. So, but special angles you're actually supposed to know quite well. Now, recall what I said earlier, since e 2 pi over 3I is equal to minus a half plus root 3 over 2I, we know this is the conjugate, hence exactly the same but with a negative for the imaginary part. Now we're going to simplify our question. So just recall that we did evaluate e to the 2 pi over 3I as minus half plus root 3 over 2I. So we substitute that in here and we substitute the conjugate in here. Now, very important from earlier, if we have minus e ln 5, or let's say rather e to the minus ln 5, the minus will go as exponent and we'll get 1 over 5, and that answer will just be 1 over 5. We drop the e and the ln. So here the same, we have e to the ln 5, but we drop the e and the ln, we just get 5. We drop the e and the ln, we just get 1 over 5. From here, we're just gonna distribute. Remember that we have the 1 over 2I in front, the coefficient of the whole bracket. Now we're just gonna distribute. That I don't have to explain, that is grade 9. Should all be fine with that. Just to recall that if you times a fraction by fraction, you times numerators together, denominators together. But that's grade 9. I don't think anyone will have a problem with that. Now I just get my LCD for these two, which is 10. So I end up getting 24 over 10. And then I get my LCD for the imaginary parts, also 10. So I get that. Then what I want you to remember we never want the imaginary in the denominator. So if we times by minus I over minus I, we get negative I. So from now on you can study 1 over I is negative I. And there is our final answer. And who would have thought that this answer will actually be in this standard complex form? So let's just recap what we did there. We did sine of a complex number because we have the real part plus the imaginary part. Now what we are going to do, we're going to do the ln of a complex number. Just to recall, in first year we would just do ln of a real number. We always mentioned that your x, the domain, must be greater than 0 and real numbers, but now we do ln of a complex number. So we are going to use ln of a complex will be this formula. So it's ln modulus plus I arc z plus 2 pi n or k. So the steps, what do you see immediately? We need the modulus, we need the argument. To get the modulus and the argument, recall now that this is your z. It's very important which quadrant you're working in. And since x is -3 and y is √3, so x negative, y positive, we are working in quadrant 2. So just remember, to get an angle in quadrant 2, we will always say pi minus your acute reference angle. So for the modulus r, what do? We just do the square root of x squared plus y squared, which is square root 9 plus 3, square root 12. Now in most cases, we will simplify root 12 as I did there. But from now on, you can actually remember that we leave it like this for the mere fact that later on we need this, and then it's just best to use the ln law, so we will say a half ln 12. So it's not necessary to simplify the root 12. For the argument, for theta, we always say for argument the arctan of y over x. Now note here, very important, I only use positive y and positive x, even though x is negative. For the what reason? I'm only getting the reference angle, which must always be an acute angle. Reference angle, an acute angle is first quadrant, where both x and y are positive. So just to recall that root 3 over 3 is 1 over root 3. So I see there are plenty of students who actually don't know. It's very important. Otherwise, you're going to struggle to use these two triangles. So we have arctan y over x. Y is 1, x is root 3. So our angle must be pi over 6, or from second year. But very important, we're working in the second quadrant. How do we get an angle in the second quadrant? It's always pi minus pi over 6, which is 5 pi over 6. Now we're just going to replace, in the formula we replace our r and we replace our argument. So what is important now is to remember that as these angles are increasing, it's going to change our sketch. Just recall what I said earlier for the sketch. Doesn't matter what n is. Doesn't matter what n is. This is my real part, or half ln 12. And just be careful, I did really just an estimation, not accurate at all, because we're not allowed to use calculators. So my real part will stay a half ln 12 all the way. It's my imaginary part. Remember, this is now my imaginary part that will change for different values of n. If n is 0, I will get 5 pi over 6. But my real is still a half ln 12. So a half ln 12 and say 5 pi over 6. Say that's my value there. Then if n is 1, I will get 5 pi over 6 plus 2 pi, which is 17 pi over 6. So obviously bigger than pi over 6. So this is when n is 0. This is when n is 1. If n is negative 1, I will get negative 7 pi over 6. Hence my vertical line, the imaginary values will differ, but the real part stays the same. So the last question we're going to do is evaluate and plot the exponential, the power in complex plane. So just make sure here you have a complex to the power of a complex. For that reason, we're going to use this formula. ZW is e to the w ln z, where ln z is what we have done before. So let me just write it here. Let me just move this. So we have e w ln z, but ln z is ln z modulus plus I arg z plus 2 pi I k, and hence this formula. So what I immediately do in my first step, I let z be 1 plus I and w a quarter minus I. Now just make sure from your formula you need the modulus and the argument of z, not of w. So we have z. Recall, it's very important which quadrant you're working in. Because x is positive, y is positive, we are working in the first quadrant. So just to go over this quick, the modulus will be root 2. You can just check that for yourself. The argument is arctan 1 over 1, which is pi over 4, from our special triangle 4 pi over 4. Now we replace back in the formula. So we have e to the w, then we have our ln of the modulus plus I arc of z, and then 2 pi I w k. So best is that before you start doing more questions, to really study this formula very well. Now what we are going to do, we're just going to simplify. So look what's happening here. We have a fraction times a fraction. So we are going to FOIL, what you're all familiar with. So that is what I did here. I just FOILed that bracket. Then what I did here, I also distributed, and I got that. I'm leaving the k outside. Then just remember, you're using your exponential laws. You should be all very familiar with this. You're gonna split. So I split this so that I have this term over here, and then I have e to the power of that term, and here I've just simplified this term. Now why I did that? Because remember I said study these forms. You should also know that this is minus I, So it's right in the beginning of the theory, and you should see that this part is I, hence the I there. So it's debatable where to leave this answer, but you can leave it in this form, but to be able to sketch, it is best to express this part, which is from my second last step, in the form re to the I theta. Why? Because then I can get my radius, and I can get my theta, and I can sketch from there, because remember that is polar form for a complex number. So what I did here, so remember from before, this is just equal to 1 over 8. Then what I did here, I kept all my terms without an I together. So I used that term and I used this term because the basis is the same. I add the exponent. Then what I did, all the terms with the I, which is that, plus this with the I on the outside. I put them together. Why? Because now I basically have my radius and I have my argument. So if I let k equals 0, I will just get this as my R. Here if I make k equals 0, I'll get that. So my argument will be this part. Then we do k equals 1, k equals 2. You can test that for yourself. So you can pause the video and just see if you get the same radius as me every time and argument. But remember, it's difficult to sketch these accurately. It's impossible without a calculator. All you have to see is that your radius is increasing. Why? Because that exponent is increasing. It's e pi over 4. Then you get 1 over 8. E pi over 4 plus 2 pi. Then 1 over 8 e pi over 4 plus 4 pi. So your radius is increasing. That's what I want to show here. Your radius is getting larger and larger. Now look at my argument. Look at my argument. This angle is also, we don't have to worry about that, minus ln root 2 because that's constant. But this angle is also increasing. So say increasing, increasing, increasing. So at the end, because my radius and my angle is increasing, I will get a spiral. And that is the end of our video for complex exponentials, powers and logs. Just make sure that you first study the theory very well and then do the 3 examples in detail.